Good morning, dear students. Welcome back to physics session. We were on the lesson magnetic effects of electric current. In the last class, we studied about the magnetic field around the circular loop and also studied about solenoid and electromagnets. Today, we are going to discuss about force on a current carrying conductor in a magnetic field. We learnt that electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on the magnet placed in the vicinity of the conductor. See here, children, whenever we know that the current carrying conductor produces a magnetic field. That is the known factor, isn't it? Current carrying conductor produces a magnetic field. The field produced magnetic field exerts a force on the magnet placed in the vicinity of the conductor. It will exert a force on the conductor. That we have to know about it. A French scientist, André-Marie Ampère, suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. Current carrying conductor will experience force when it is kept in the magnetic field. So that is the special thing we have to understand. The force due to the magnetic field acting on a current carrying conductor can be demonstrated through this activity. It can be that whatever the scientist Ampere showed, that can be experimentally proved by this experiment, demonstrated through this activity. A small aluminum rod is taken. Let us go through that activity. There is a small aluminum rod AB. You can see, I think, AB rod is taken and about 5 centimeter in length. Using two connecting wires, it is suspended horizontally from a stand. It is suspended. Actually, in the first it was horizontally suspended. Afterwards, it is displaced. Okay, the AB was horizontally suspended to a stand. Place a strong horseshoe magnet. You know the horseshoe magnet. Here it is the horseshoe magnet. You can observe, children. This is the horseshoe magnet. It is placed in such a way that the rod lies between the two poles with the magnetic field directed upwards. Magnetic field directed upwards. It is placed in between the two prongs of this horseshoe magnet is there. No, that is takes in between. The aluminum rod will be in between these two poles. In such a way it is kept, but here the support is not shown, children. Actually here support must be there to keep the horseshoe magnet. It is not shown in this diagram, okay? But we have to keep that on any support, the horseshoe magnet. Then the aluminum rod is connected in series with a battery, plug key, and a rheostat also you can use to change the current. Also rheostat, variable resistance we can use. Here the aluminum rod, this AB is the aluminum rod, that is the connected in series with the battery, key and a rheostat. Now observe, children, here this is positive terminal of the battery. Here it is negative terminal of the battery. Always conventionally the current flows from positive terminal to negative terminal, right? Positive terminal to negative terminal. Conventionally it is always from positive to negative, right? Let us pass current through the aluminum rod from B to A. Observe, children, here AB is the rod, aluminum rod. Now the key is plugged. The current is passing through the circuit. Started passing from positive to negative. Observe, children, here positive, here arrow mark, and goes here and again comes to point B and then to A. So from B to A current is passing and goes to negative terminal. From positive to negative terminal current will flow. Observe children, always from positive to negative. Here you can see the arrow mark here, and it is ending at negative terminal. So always current flows from positive terminal to negative terminal, and in the sense in the rod the current is flowing from point B to A. Observe children, what we can observe here now, the rod is displaced towards left. That's what's shown here, children. It was displaced. Whenever current is passing from B to A, the rod AB, aluminium rod AB, is displaced towards left when the current is from B to A. Now, let us observe by changing the terminals of the battery. Negative brought here terminal, positive here. By interchanging the terminals of the battery, we can reverse the direction of the current, right? What happens then? If you want to change the terminal, here it becomes positive now. This becomes negative, right? Now what happens, children? The current will start flowing from positive to negative. Positive to negative. That means that the current is flowing from point A to B. So A to B and then to the negative side. So what happened here now? The current has changed its direction. How we can change the direction of current? By interchanging the terminals of the battery. Now in this case, when the direction of the current is reversed, what happens, children? What is observed there? We can observe that the direction of the displacement also reversed. That is towards the right side. The rod has been displaced towards right. This time it is towards right. In the beginning it was towards left. So what observation we can make? Whenever the direction of the current is changed, the direction of the force is also changed. Displacement, that is the displacement of the aluminium rod is also changed. The displacement of the aluminium rod in the above activity suggests that a force is exerted on the current carrying aluminium rod when it is placed in a magnetic field. That important point we have come across by this activity. It also suggests that the direction of the force is also reversed when the direction of current through the conductor is reversed. That we observed. I told you to interchange the terminals. Then the current changes its direction from left to right. It will be during the first instance from right to left it was flowing. In the next situation from left to right it was flowing. That means that the current has changed its direction. The direction of the current is reversed. Then we observed that the displacement also reversed. It was towards the right. In the next case, in the first case it was towards left, the displacement of the rod. In the second case, the displacement towards right. So we can infer one thing from this: whenever the direction of the current is reversed, the direction of the displacement, that is the force acting on the rod, is also reversed. Now let us try changing the magnetic field, direction of the magnetic field. How we can change the direction of the magnetic field? Here, which is producing magnetic field? Horseshoe magnet. This we will interchange the poles. Vertically we will reverse it. South comes below and north goes upwards, such that it is reversed. The poles are reversed, children. Here, this is brought here. South pole brought here. North pole is here. In the beginning, north pole was here. Correctly, I wrote here. South pole was here. In the next situation, I will change the vertically interchange the poles. Here comes south, here comes north. Then what is observed? It is once again observed that the direction of the force acting on the current carrying rod gets reversed. Here also the same thing observed. It shows that the direction of the force on the conductor depends upon the direction of the current and the direction of the magnetic field. What you can observe, children, we tried changing the direction of the current. There also we observed the force acting on the conductor reversed. And then we tried interchanging the poles of the magnet. That means that we are changing the direction of the magnetic field. Then also the displacement in the rod is reversed. So this is observed that the direction of the force on the conductor depends upon the direction of the current and the direction of the magnetic field. So these three factors, which factors? Magnetic field, the current and the force. These three are related. These three factors. Which are the factors related? The current, the direction of the current, direction of the current, the direction of the magnetic field, and the direction of the displacement. Displacement means we can take it as the force acting on, the force on the conductor or motion of the conductor. Force on the conductor or motion of the conductor. We can consider this factor as motion of the conductor. So here these factors we can observe, children. What are the three factors related to each other? By this activity what we can understand? The current, magnetic field and the force. These three factors are related to each other. They depend on each other. When one is increased or one is changed, one factor is changed, other factor is also changed. It is experimentally observed that when the direction of the current is at right angles to the direction of the magnetic field, the displacement of the rod is the largest, highest when it is perpendicular, when it is right angles to each other. When the force on the conductor is the largest or the highest when the direction of the current is at right angles to the direction of the magnetic field. That is, these two factors are there, no? Magnetic field and force on the, that is current. When these two factors are perpendicular, when they are right angles to each other, we can observe maximum force or maximum displacement in the conductor. In such a condition, we can use a simple rule to find the direction of the force on the conductor. To know the direction of the conductor, we can use one rule is there, that is known as Fleming's left hand rule. Children, we were studying about the relationship between three factors: current, magnetic field, force on the conductor. If there is a current carrying conductor kept in the magnetic field, experiences force. That principle we can use here, children. Always, what is the principle? A current carrying conductor kept in the magnetic field experiences force. By this activity, we can understand, we can infer that principle. Always there will be a force acting on the conductor which is carrying current kept in the magnetic field. That factor is there, no? That we can show the directions. In which direction? It is confusing, no? In which direction magnetic field is there, current is there, force will act in which direction? For that all, there is an answer by a rule formulated by Fleming. Fleming's left hand rule. That is known as what? Fleming's left hand rule, children. Fleming's left hand rule gives answers for the directions of all the three factors. Left hand rule. It is a Fleming's left hand rule. It gives the direction of these three factors, these three parameters: current, magnetic field, force on the conductor. It is given by which rule? Fleming's left hand rule. How we can use a left hand rule, children? How we can identify, how we can understand about the directions? See, stretch your left hand. Stretch your left hand. See here. It is your left hand. Right hand, left hand. So, stretch your 3 fingers of your left hand. 3 fingers, which all the fingers there? This is what it is known as, this is a thumb or main finger. This is also known as a main finger, thumb. This is, what is this? This is the forefinger. This is forefinger. This is middle finger, forefinger or index finger also we used to say. This is middle finger. Middle finger, forefinger and the thumb. Which are they? First, we have to stretch 3 fingers of our left hand. Which are all we are stretching, children? Thumb, the forefinger. Write the spelling F-O-R-E, children, not F-O-U-R. Forefinger and the middle finger. These 3 fingers. Using these 3 fingers, we can understand the directions. We can easily, in any situation, we can easily know the directions of these 3 parameters: current, magnetic field and force on the conductor. How we can state Fleming's left hand rule? See, when we stretch the 3 fingers, thumb, forefinger and the middle finger of our left hand such that perpendicular to each other, those must be perpendicular to each other, then the forefinger indicates always, you can observe, children, what it indicates? It indicates magnetic field. Always it indicates a magnetic field. Forefinger indicates magnetic field. And the middle finger indicates current. You can observe, children, here. It is current here. The forefinger indicates magnetic field. The forefinger indicates magnetic field. The middle finger indicates the current. So, when we stretch, how to state, let us see. When we stretch the 3 fingers, the thumb, forefinger and the middle finger of our left hand such that the forefinger indicates magnetic field. Forefinger indicates magnetic field. The middle finger indicates the direction of the current. The middle finger indicates the direction of the current. Then the thumb indicates direction of motion of the conductor or direction of the force on the conductor. So in this activity, that only we saw, isn't it? 3 factors: aluminum rod experienced motion, and the magnetic field produced by the horseshoe magnet, and the current through the battery. So these 3 factors are under consideration. So we are formulating the law of Fleming's left hand rule to know the directions of these 3 factors. Here you can observe magnetic field, force and current are shown here. Magnetic field always shown by forefinger, and the current is indicated by middle finger. The force experienced by the conductor, that is thumb. Thumb indicates force on the conductor, like this. Clearly observe now how to state the Fleming's left hand rule to know the directions of current, magnetic field and force experienced by the conductor. Now, when we stretch the 3 fingers, thumb, forefinger and the middle finger of our left hand such that they are perpendicular to each other, then the forefinger indicates the direction of the magnetic field. The middle finger indicates the direction of the current, electric current. Then the thumb indicates the direction of the force experienced by the conductor. The force experienced by the conductor or motion of the conductor. In this way, you have to state the law, Fleming's left hand rule. Very important rule. You may be using for some sums to solve. Okay. Once again, I'll repeat. Fleming's left hand rule states that when we stretch the three fingers of our left hand, thumb, forefinger and the middle finger of our left hand such that they are perpendicular to each other. Set them as perpendicular to each other, children. See here, perpendicular to each other. They must be like this. Here observe. Here you can observe they are perpendicular to each other. Here it is shown they are perpendicular to each other. Then the forefinger indicates the direction of the magnetic field. The middle finger indicates the direction of the current. Then the thumb indicates the direction of the motion of the conductor or the force experienced by the conductor. Three directions we can know easily using Fleming's left hand rule. I hope you understood. Once I will have a glance on it. Fleming's left hand rule states that when we stretch the three fingers, thumb, forefinger and the middle finger of our left hand such that they are perpendicular to each other, then the forefinger indicates the magnetic field, the middle finger indicates the direction of the current, then the thumb indicates the direction of the motion of the conductor or the force experienced by the conductor. This is known as Fleming's left hand rule. This rule may be useful in some devices also. The current carrying conductors, magnetic fields needed. Yesterday in solenoid, we talked about that. There all we need the law to understand the directions of magnetic field, the current and the force. Devices like electric motor, electric generator, loudspeakers, microphones and measuring instruments all use the current carrying conductors and magnetic fields. These devices use the current carrying conductors and magnetic fields and thereby they are experiencing mechanical force. That is also known as mechanical force. The motion of the conductor can also be known as mechanical force. So, I hope you understood the Fleming's left hand rule. Let us once have a quick glance on the Fleming's left hand rule. The three fingers of our left hand are stretched. The thumb, forefinger and the middle finger are stretched such that they are perpendicular to each other. Then the forefinger indicates the direction of the magnetic field, The middle finger indicates the direction of the current and the thumb indicates the direction of motion of the conductor or direction of force experienced by the conductor. This is Fleming's left hand rule. I hope you understood. So that can be shown in this way here. Magnetic field, force and the current. So now let us have a try to solve one more problem here given about to know the direction in the textbook. See here 13.2. An electron enters a magnetic field at right angles to it as shown in the figure. It is shown here. You can observe, children. The direction of force acting on the electron, the force experienced by the electron, you have to find out. Options are given to the right, to the left, out of the page, into the page. They have given like that. In which direction the force acting on the electron will be? What is the question now? They have given that an electron. See here, children, an electron enters. This is the direction of magnetic field. This is the direction of a magnetic field. You can observe here. And here there is an electron. They gave perpendicular to each other, at right angles to each other. The direction of the electron, the direction of the magnetic field. They have given 4 options, to the right, to the left, out of the page and into the page. How we can understand the directions using Fleming's left hand rule here? We can understand that, children. Using Fleming's left hand rule, we can say the direction of the force experienced by the electron. Always remember, children, conventionally it is the direction of the current will be opposite to the direction of the electron always. Conventionally it is positive to negative, children, always. But electron, it is reverse direction. So electron is moving in this direction, means that if electron is moving downwards, means that the current is flowing in the upward direction, children. Remember always, because the direction of the current will be opposite to the direction of the motion of the electron. So this will be the direction of the current, isn't it now? According to that, it will be the opposite to that. So electron, if it is moving like this downwards, the current will always be opposite to that. That is the direction of the current. And magnetic field, in this way, we have to find out what now? We have to find out the direction of the force experienced by the electron or motion of the electron, in which direction it is moving. So let us take the help of Fleming's left hand rule to know the direction of the electron. Now stretch your left hand such that this is the rule, isn't it? Magnetic field, current, and this is a current, isn't it, children? This is current. This is a magnetic field. This is motion of the conductor. Now we are stretching like this actually, isn't it? For application of the Fleming's left hand rule for this. Now let us consider how these are moving now. How we can consider this now? See, children, here. Here, now if I stretch the fingers like this, you can adjust to the situation. You can say like this. You can say like this. The rules can be applied in any way, holding your fingers in different ways, but perpendicular to each other. Now I have to hold the fingers like this, right? Because this is upward direction. Here you can see the direction of the current is upward direction, children. Correct? So this is the direction of the current. This is the direction of the magnetic field. Here you can observe, children. This is the direction of magnetic field. Then what is the direction of the motion of the conductor? What is the direction of the force experienced by the electron, children? You can observe here it is into the page, towards the page. Can you see? It is towards the page. Correctly observe how to apply Fleming's left hand rule for this sum. An electron, it is entering into a magnetic field. You can observe electron direction is this one. Movement of electron is towards downward direction, but the current will be always opposite to that, upward direction. Okay. Then magnetic field will be towards right. So what is the force experienced by the electron? The direction you have to find out. Hold like this your fingers, because this shows the direction of the magnetic field. Here magnetic field, magnetic field. You can see, children. This is upward direction. What is this upward direction? This is a current. So what we want to know this one only now. Motion of the conductor or the force by the electron. What is the force acting on the electron? In which direction? Into the page, children. See, this is page. Into the page it is directed. So it is into the page. So the option is, which one is correct? Into the page. Inside the page. That is into the page. It is moving. Hold like this. Magnetic field, current, and the motion of the conductor. So the electron will be towards the into the page. So that the option is correct here. The option is into the page. It is right according to the Fleming's left hand rule, children. Magnetic field, current, and the motion of the conductor. That is experienced, force experienced by the conductor. It is into the page. So the option which is correct, to the right they gave, to the left they gave, out of the page they gave, into the page they gave. No, it is into the, that is last one only correct. Into the page. So this is the option, correct option. I hope you understood how to know the directions. If two directions are given, another direction we can find it out, children. Hope you understood. Okay then.